All right, 12.2. This is just a review of the previous lesson. So we have 128 students. Always want to know the total. And if it's not given to you, all you need to do is add these up. Okay, so sometimes you'll just be given the table and you may not know what to do. First step, always add and find out how many people there are total. Just like on a test, like I referred to in the previous lesson, you always want to take your grade out of the total number of points. So you need the total number of people. So, what's the probability you would randomly choose a lacrosse person? 20 over 128. And again, you don't have to reduce that. You can if you want, but I would say don't waste time reducing it when you could have possibly accidentally reduce it wrong. So that's an appropriate answer. Or you can turn it into a decimal, which is 0.15625, or percent, 15.625%. And since rounding is an issue, let's just talk about that. If you rounded it to the 100 spot, that would be 0.63%. And if you rounded it to the 10 spot, that would just be 0.6%. And then one more, baseball or basketball. Now, this is a tricky one. When you see this word or, you're basically increasing your odds because you're taking either one, baseball or basketball. So in that case, we're actually going to add them together. So baseball is 25, basketball is 48. So we're going to do 25 plus 48 over 128, which is 73 out of 128. And again, we can turn that into a decimal by dividing by 128 and get 0.57. That's not a 7. There's a 3 eventually, so I'm not just making this stuff up. It's 5703. It goes on for a while. So we'll leave it at that. Or 57.03%. Now again, talking about rounding, this is one I would not round to the 10 spot because you'd have to remember to put 57.0. If you were not told where to round, I would round to the 100 spot just to show that it wasn't 57 whole numbered. All right, probability of independent events. Okay, 2 events are independent if and only if the probability that both events occur is the product of the probabilities of the events. So if both are going to happen, you find out the probability of one and multiply it by the probability of the other. And basically that makes it harder to occur, but that makes sense because you have the probability of one event happening. Okay, that's fine. You have the probability of the other event happening, but for it both to occur at the same time, that should be less likely, and that's what happens when you multiply 2 decimals. So, students taking the quiz randomly guesses 4 true-false questions. Okay? Use the sample space to determine whether guessing question 1 correctly and 2 correctly are independent events. Okay, so there's going to be a little bit of time saving here. You're going to need to look back to your notes from section 1, example 2, when we made that chart of all the outcomes. Remember there were 16 outcomes? Okay, and then look now to find out the probability for question 1 and the probability for question 2. So correct on question 1 and count those up. So go through the chart and look how many times question 1 was correct and how many times question 2 was correct. Okay, look at that real quickly and then hit pause right now, look at that, and then come back. Welcome back. Okay, so we're going to have the probability of, I'm just going to put C instead of writing the whole word correct, on 1. And you should have counted up 8 out of 16 chances. And the probability of getting number 2 correct was also 8 out of 16. All right? So, the probability of correct 1 and correct 2 is going to be these two multiplied by each other. All right? So, in this case, it would be easier, to reduce. This is 1/2 and this is 1/2. So you're going to do 1/2 times 1/2, which is 1/4. Or if you did 0.5 times 0.5, you get 0.25, which is 1/4. And also you could write it as 25%. Okay, so there's a 25% chance that both happen. And since that's the case, they are independent events. In other words, it doesn't make sense really in this question, what I just said probably, but let's say I said, I believe there's a 20% chance of them happening independently. Well, when you do the math, you find out it's a 25% chance. So 20% chance would not work out for independent. It has to be the product. So in this case, 25% shows they are independent events. Okay, number 2. A group of 4 students has 1 boy and 3 girls. Teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Look at the sample space provided to determine whether randomly selecting a girl first and selecting a girl second are independent events. So let's look at this. You've got your chart of number girls 1, number girls 2. All right. Now, how many are there total? Well, total, there's 12 in sample space. Okay, so that's going to be our denominator. Now, we need the probability of a girl in first place, in the first spot, and the probability of a girl in the second spot first. So how many times is a girl in the first spot? Okay, so we're going to count those up. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Basically, girl in the first spot. Okay? And then the numbers just mean girl 1, girl 2, or girl 3. Okay? So there's 9 chances when the girl came in first spot. Now, what about the girl in the second spot? Well, that's these 3 and those 1, 2, 3, 4, 5, 6. So that's also 9 out of 12. So the probability of both is going to be 9/12 times 9/12. But again, I would probably reduce this to 3/4 just to keep my numbers smaller, a little easier to work with. So 3/4 times 3/4 is 9/16. Which is 0.5625, or 56.25%. Now, that's what the number needs to be if they're independent. Let's see what it actually is on the chart. Okay, so looking for a girl first and a girl second. So girl first and girl second is those 3 and these 3. Well, that is 6 out of 16, which is not 9 out of 16. So the answer is no, not independent. Again, to be independent, it would have to be the probability of 1 and the probability of 2 multiplied, which is this number, or this fraction. And when we actually look at the table, we got this fraction. Since they do not match, then the answer is no. Okay, now we have the probability of dependent events. In other words, the second thing is dependent on the first thing. Okay, so like if I pull letters out of a hat and I don't put the letter back in, then the odds change because now the numbers are different on the second pull. So let's look at this example. First off, the probability of A and B, okay, given the first event, is the probability of A times the probability of B given A. And this will make sense when we kind of do it in the examples. So looking at example 2 that we just did, probability of a girl first and a girl second. Well, first you take the probability of girl first, which was 9 out of 12. Then a girl second, given that we had a girl first. Because once you pick that girl, she's not in the running. So it actually changes the numbers. So that's 6 out of 9, and therefore that's 1/2. A little confusing at first, I understand. It'll make more sense as we dive into it. Okay, as part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability you get a 5 on the first spin and a number greater than 3 on your second spin. Now, this is just a regular old independent event again because we're not ruling out anything given the first spin. So our first spin is, what are the chances of getting a 5 in your first spin? Well, the probability of 5 is 1 out of 8. Now, what's the probability of a number greater than 5? So the probability of x greater than, 3. My bad. Greater than 3. Well, how many is that? That's 4, 5, 6, 7, 8. That's 1, 2, 3, 4, 5. 5 out of 8. Okay? So the probability of both occurring is 1/8 times 5/8, which is 5/64, or 0.078 or 7.8%. Straight independent, because spinning a 5 does not affect spinning again and getting a 5 possibly, unless you actually took that number off the board. Like, you're not allowed to get the same number twice. Okay, now in example 4, we got a bag containing 20 $1 bills and 5 hundreds. You randomly draw a bill from the bag. You set it aside. This is a dependent event, because once you set it aside, the numbers change. Find the probability that both events A and B will occur. First off, the first bill is a $100 bill. Okay? So first off, how many bills are there? There are 25 bills in the bag. Okay? Now, your chances, the probability of event A getting a $100 bill is 5 out of 25. Now, the probability of B, okay, you're getting a second $100 bill. Well, if you put it aside, how many bills are left in the bag? There are hundreds. There are only 4. Also, there's not 25 in there anymore. There's 24. Okay? And I'm sorry, I forgot to write the special designation. There should be probability of B given A, because A has occurred. That's what that line means. Once A has occurred, it changes the odds of B. Now, it says find the probability that both will occur. So that's that new formula. The probability of A and B is the probability of A, which in this case is 5 over 25, times the probability of B given A, which is 4 over 24. When you do that and reduce it, that equals 1 out of 30, or 0.033, or 3.3%. So a very small chance of getting two $100 bills in a row. Okay, example 5. You randomly select 3 cards from a deck of 52. What's probably all 3 cards are hearts. First, when you replace each card. Second, when you do not replace each card. Okay, so we're going to do situation A first. That's basically independent. Very simple. Okay? So the possibility of getting a heart, well, there's 13 hearts out of 52. And if you put it back in, there's 13 hearts out of 52. And if you put it back in, there's 13 hearts out of 52. And you basically just multiply these. And when you do that and reduce it, it comes out to be 1 over 64. Or 0.016. 1.6%. If you don't want to deal with the fractions and all that reducing, which is not too bad because 13 actually goes into 52. So this goes into 52 4 times, this goes into 52 4 times, and I'm just making it fun, 4 there. And so it ends up just being 64. But if you don't want to deal with that, you can just turn 13 over 52 into a decimal and multiply that. Okay? Now that was easy. But on B, what you have is, you first have the possibility of getting a heart, which we said was 13 out of 52. But then you take out a heart, there's only 12 left, and there's only 51 cards left. And then there's only 11 hearts left and 50 cards left. So when you multiply all these out, you get a nasty number, 11 over 850, which ends up being 0.013 or 1.3%. Okay, almost there. Example 6. Quality control inspector checks for defective parts. The table shows the results of his work. Find the probability that a defective part passes and probability that a non-defective part fails. So this one's kind of tricky. First off, we're talking about the probability that it passed, but given that it was defective. Okay? So, how many passed were there that were defective? 3. How many were the total defective parts? 39. Okay, so that is 0.077 or 7.7%. Okay, and it's just about how you read the chart. Then we're talking about the probability of it failing given that it was non-defective. All right. So in this case, how many non-defective fails were there? 11. How many total non-defectives were there? That's 461, which works out to be 0.024 or 2.4%. And here's our last example. At school, 60% of students buy a school lunch. Only 10% buy lunch and dessert. What's the probability that a student who buys lunch also buys dessert? Okay, so remember, probability of B given A is the probability of A, and B divided by the probability of A. Okay, so first off, the probability of students who buy lunch and dessert, both, okay, is 10%, 0.1. And the probability of students who just buy lunch is 0.6. So if you divide that, or change it to 1/6 if you want to, either way, you get 0.167 or 16.7%. And that's it.